Now we'll start a new topic from abstract algebra. This is relation, and this topic is important for IIT Joint Entrance Examination, HS level, and SSC, NVS, KVS, as well as it is important for the graduation course, especially in CU. And in the syllabus, it is given an equivalence relation, equivalence classes and partitions, and it is from the paper code MHCC 2102. And whatever we'll do here, the problem and solution, that is basically from the K Mapa book. So first we'll start a few concept in relation, then we'll continue some problems. So our first recall. This is related to the definition of relation. Definition of relation. So let we consider, let A be a non-empty set. A relation, we consider the symbol rho on A is a subset of, A Cartesian product A. So what exactly mean by that? Relation is a subset of A Cartesian product A. That is, we can write relation rho is subset of A Cartesian product A. Now, here we will think about some important note. Note 1. Relation rho is a subset of A cross A. What is A? Where A is non-empty set. Where A is non-empty set. And also you will recall one important definition. What is meant by the Cartesian product A cross B? A Cartesian B, that means it is set of all ordered pairs AB, where A belongs to capital A and B belongs to capital B. So now, our second note, that means note 2, rho bar, this is also a subset of A cross A. Rho bar is basically represent not related. Now we'll come to another important definition is here. If A is basically non-empty and B is also non-empty, so what is meant by the relation between two sets? Relation between two sets. So here let we consider A and B are both non-empty sets. A is non-empty and B is also non-empty. So our relation rho on A and B, this is also a subset, of A Cartesian product B. Or you can say that is rho is a relation between A and B. It is a subset of A cross B. So now here again the important note, rho is a subset of A cross B. If there is rho bar, that means not related, this is also subset of A cross B. The third property is important, very very important, rho and related and not related, that two set, if you take the unions, it is exactly A cross B. So now we will come to one example, and from example you will understood what is exactly meant by this definition. So talking about example, so let A equals to 1, 2, 3, 4, 5, and this is a non-empty set, and B equals to 11, 12, 13, 14. Now we will define a relation between A and B. So here the relation between A and B, the relation rho is defined by specifying that an element A belongs to an element small a belongs to capital A is related to an element B belongs to capital B if A divides B. So now you need to define the relation, and we'll examine how the relation is a subset of A cross B, not related. This is also, that set is also subset across B, and how the union will be A cross B. So here the explanation corresponding to the example. What is exactly given for the set A? So here A equals to 2, 3, 4, 5 and B equals to 11, 12, 13, 14. Now what is the relation? It is defined on AB. So rho is defined as rho equals to all those ordered pair AB belongs to A cross B such that A divides B. Now we will come to the set. Therefore rho equals to, okay, here A belongs to capital A and B belongs to capital B. So now start from the first element. In A2, 2 divides 11. No. This is not related. So 2 does not divide 11. So 2 and 11 comes here. Now 2 divides 11. No. 2 divides 12. Yes. So 2, 12 comes here. Now move to the 3. 3 divides 11. No. This comes here. 3 divides. Okay, first we'll finish 2. 2 divides 11. No. 2 divides 12. Yes. 2 divides 13. No. 2 divides 14. Yes. That will come here. 3 divides 11. Now we'll start from 3. 3 divides 11. No. That will come here. 3 divides 12. Yes. This will be comes here. 3 divides 13. No. 3 divides 14. No. Now we'll come to the 4. 4 divides 11. No. 4 divides 12. Yes. That will come here. 4 divides 14. No. Now start from 5. 5 divides 11. No. 5 divides 12. No. 5 divides 13. No. And 5 divides 14 again. No. So if it is divide, that means it is related, that comes under the set row. And if it is not divides, that means it is not related, so that comes under the row. What will be your observation here? Your observation, the first observation, rho is a subset of A Cartesian product B. Second observation, rho is also subset of A Cartesian product B. Third observation, rho intersection rho bar, this is basically 5. And fourth observation, rho union rho bar, this is the Cartesian product A and B. So for any relation, you will see this kind of features. So here I just add one more result, rho intersection rho bar, this is basically 5. Similarly here, Rho union rho bar, this will be A Cartesian product. And 4, rho intersection rho not related. Related intersection not related, so that will be 5. Now we come to the different types of relation, and we'll try to know about the equivalence relation here. So types of relation. Types of relation. On a set, on an unempty set A. So what are the types? First we will know the reflexive relation. Reflexive relation. When a relation is called reflexive relation, so here the definition is, let A be a non-empty set and rho be a binary relation on A. Then A is called reflexive relation. Rho is called reflexive relation if A rho A holds for all A belongs to A. That is, if A comma A belongs to A for all A belongs to A. Now we come to the symmetric relation. Next is symmetric relation. So the common thing is A is non-empty set and rho be a binary relation or relation on the set A. So here then rho is called symmetric. Rho is called symmetric relation if A rho B and A rho B, that implies B rho A for all AB belongs to A. If A rho B holds, then B rho A holds. If you prove that, then it will be comes under the symmetric. That relation for all AB belongs to A. And there is another relation. This is called transitive relation. Transitive relation. So rho is called transitive if A rho B and B rho C, that implies A rho C for all ABC belongs to A. So this is the definition of transitive relation. Because in the first case, if you start A, so then A is related to A. This is the figure is like this, one kind of loop. Here this is A and this is B. So if A is related to B, then B is related to A. That you need to show. In the third case, here is A, here is B. If A is related to B and B is related to C, then you need to show A is related to C. Okay. So this part is A related to B. This is B related to C. This is A related to C. This part is A related to B. This is B related to A. And here A is related to A. Okay. So now we'll come to some notation. Note, when you will see A related to B, that if and only you can say AB belongs to rho. And if you see A is not related to B, that you can write A comma B belongs to rho bar. Okay. Or you can say A comma B does not belongs to So these are the few types of relation: reflexive, symmetric, and transitive. Reflexive you can represent R, symmetric you can represent S, transitive you can represent by T. Now we come to the definition: equivalence relation. So a relation rho on a non-empty set A is called equivalence relation if it is reflexive, symmetric, and as well as transitive. So our next definition that you can say our recall 3. So when a relation on a non-empty set is called equivalence relation, this is about equivalence relation. Let A be a non-empty set and rho be a relation on A. Then rho is subset of A cross A. Then rho is called equivalence relation if it is a reflexive, then it is symmetric, and third, it is transitive. So what is the meaning of the reflexive? A rho A for all A belongs to A. What is the meaning of the symmetric relation? A rho B, that implies B rho A for all AB belongs to A. What is the transitive relation? A rho B and B rho C, that implies A rho C for all ABC belongs to A. Okay. So or here you can say that is A comma A belongs to rho for all A belongs to A. Here you can say A comma B belongs to rho implies B comma A belongs to rho for all AB belongs to A. And here you can write A comma B belongs to rho, B comma C belongs to rho, that implies A comma C belongs to rho, as you wish. See, different writers, they are using different kinds of notation. And if this three holds, then the relation is called equivalence relation: reflexive, symmetric, transitive. So equivalence relation, that means reflexive, yes; symmetric, yes; transitive, yes. So RST. Now we will come to some important problem on the relation chapter. So our first problem is problem number 1. A relation rho is defined on the set Z. A relation rho is defined on the set Z by A is related to B if and only if A minus B is divisible by 5. You can think about with respect to position of 5, 6, 7, 8, 9, whatever, any kind of natural number, where A comma B are basically integer. What is your question? Question is, examine if rho is an equivalence relation on Z. Rho is an equivalence relation on the set of integers. It is equivalence relation or not, that you need to examine. So that means we will examine reflexive, symmetric, and transitive. So now the problem is how to solve this problem. So first you will add here the relation rho is defined on the set Z by A related to B if and only if A minus B is divisible by 5. What is AB? Where AB belongs to Z. Now we come to one by one. First we will prove it is reflexive or not, then symmetric or not, and after that we will prove transitive or not. So first one is about reflexive. So we will take any A belongs to Z, any integer. And then you will check what will be your A minus A. So this will be 0, and 0 is always divisible by 5. No problem. So if A minus B is divisible by 5, that implies A row B. So A minus A is divisible by 5. This is basically A row A. So what happened here? A row A, that is holds for all A belongs to Z, because our A is a arbitrary integer. So that means it is reflexive. So therefore, rho is reflexive on Z. Now we'll do the second thing. It is symmetric or not. So how will write? Let A comma B belongs to Z be such that A row B holds. So now I will show A row B to B row A. That I will show. So what exactly mean by A row B? A row B means A minus B is divisible by 5. That is A minus B is divisible by 5. So that means A minus B equals to 5k for some integer k belongs to Z. But we need to show B row A. That means B minus A is divisible by 5. How you will show B minus A is divisible by 5? So here just you take the minus sign, B minus A, that will be 5 into minus k. Now since k is an integer, so minus k is also an integer. So that means B minus is divisible by 5. So B row A holds. We have taken any two arbitrary integers where A row B, that implies B row A. That means A row B implies B is related to A for all AB belongs to Z. So that means row is symmetric on Z. So therefore, row relation is symmetric on Z. Now we will come to the third point. That is about transitive. So what we will assume? Let A comma B comma C belongs to Z be such that A row B and B row C holds. So what happened? Now we will show A row B and B row C. From this I will show A row C. So A row B means A minus B is divisible by 5. And B row C means B minus C is divisible by 5. So what exactly mean by this? A minus B equals to 5k1 and B minus C equals to 5 into some k2. What is k1, k2? For some k1, k2 belongs to integer. So what I will show? I will show A row C. That means I will show A minus C is divisible by 5. That means I will show A minus C equals to 5 into some integer. So I will add this to relation. So what I will get? A minus B plus B minus C. That will be 5 into k1 plus k2. In that case, it will happen 5 into K1 plus K2. It is divisible by 5 as K1, K2 both are integer. So that implies K1 plus K2 is also an integer. So that means what we get? We get A row B and B row C, and that implies A row C. So that means A row B and B row C implies A row C is related to C for all A, B, C belongs to Z, because our choice was arbitrary. So that means rho is transitive on Z. Now we come to the point, since rho is reflexive, symmetric and as well as transitive. So thus we conclude, since rho is reflexive, symmetric and transitive relation on Z, so rho is an equivalence relation. Equivalence relation on Z. So this is proved. So you examine here, rho is an equivalence relation. Now you have given an homework in position of 5, you can take any natural number. So you have given the question, a relation rho is defined on the set Z by A row B if and only if A minus B is divisible by N. Is divisible by N for all AB belongs to Z. So here you will examine or you will prove that what is your N? N is basically a natural number. Or you can take integer, no problem. Prove that rho is an equivalence relation on Z. Now you may be asked this kind of question. This is your exercise. You may be asked this kind of question as an MCQ type. Let rho be an relation on Z defined by A row B if and only if A minus B is divisible by M for all AB belongs to Z and M is a natural number. Then which of the following is true? Option A, rho is reflexive, symmetric but not transitive. Option B, rho is not reflexive but symmetric and transitive. Option C, rho is reflexive, transitive but not symmetric. And option D, rho is reflexive, symmetric and transitive. That means rho is an equivalence. So option D is correct. All other options are false. Now we will continue the next important problem here. So it is given a relation rho on the set Z. A relation rho on the set Z be defined by is related to B if and only if 2A plus 3B is divisible by 5. What is AB? For all AB belongs to Z. And the question is examine if rho is an equivalence relation on Z. That you need to examine. How you will examine this kind of problem? So first we will come to the solution. Here the relation rho on the set Z is defined as A rho B if and only if 2A plus 3B is divisible by 5 for all AB belongs to Z. Now we come to the equivalence. That means first we will check it is reflexive, second symmetric, and third transitive. So we will take let A belongs to Z, then 2A plus 3A. So what will be the value? 5A, and which is divisible by 5? Which is divisible by 5. So that means if 2A plus 3 is divisible by 5, that means A related to B. That means they are A related to A. So therefore A related to A holds for all A belongs to Z, because our A was arbitrary. And that implies rho is reflexive on Z. Now we come to the symmetry point. Symmetric relation. What will let A comma B belongs to Z be such that A rho B holds. So then from A rho B will show B rho A. So now the question is how it will show. So what is exactly the meaning of A rho B? So A rho B means 2A plus 3B. This is divisible by 5. What is the meaning of B rho A? This is 2B plus 3A is divisible by 5. So how we will show? So now you just check, you just add these two, 2A plus 3B and 3A plus 2, that will be 5A plus 5B. So here we can write 2A plus 3B is divisible by 5, that means it is basically 5K for some K belongs to integer. So now what we will do? So here we can write, we know the 5A plus 5B is divisible by 5. So 5A plus 5B minus 2A plus 3B. So that will be 5A plus B minus 5K. So what will happen here? So this is basically 2B plus 3A. That will be 5 into A plus B minus K. Now since A, B, K all are integer, that implies part A plus B is integer, minus K is integer, so A plus B minus K must be an integer. So that means 2B plus 3A is divisible by 5. So what we proved? We proved A rho B, that implies B rho A. Since A, B are arbitrary, so therefore we can write A rho B implies B rho A for all A, B belongs to Z. And hence thus rho is symmetric relation on Z. Now we will come to the third. So symmetric relation is proved. Now we need to prove it is transitive or not. So what we consider? We consider ABC belongs to Z be such that A row B and B row C holds. So now start from A row B and B row C. And from that we can imply, you will imply A row C. So what will happen here? What is the meaning of A row B? 2A plus 3B is divisible by 5. What is B row C? 2B plus 3C is divisible by 5. What will show? Will show A row C, that means 2A plus 3C is divisible by 5. How will show? So since 2A plus 3B is divisible by 5, so what will be the value of 2A plus 3B? That will be 5K1 for some K1 belongs to Z. And 2B plus 3C, that will be 5K2 for some K1 comma K2 belongs to Z. So now we'll add this to value. What will happen? 2A plus 3B plus 2B plus 3C. If we add these two, that will be 5K1 plus K2. From that, just in 2A plus 3C, that will be 5 into K1 plus K2, and here the value is 5B, that will come, so it will be minus B. So that means 2A plus 3C is divisible by 5 since K1 plus K2 minus B, this is basically integer. So what happened here? A row B and B row C, that implies A row C. That means A row B and B row C, that implies A row C for all ABC belongs to Z, as ABC are arbitrary. So thus, row is an equivalence relation. So here row is basically, row is transitive relation on Z. Row is reflexive, symmetric and transitive. So row is an equivalence relation on Z as it is reflexive, symmetric and transitive. Now we will come to the next problem. This is also your exercise. Similar kind of problem you you have asked in different examination. The problem is, let row be a relation on Z defined by A row B if and only if 3A plus 4B is divisible by 7. Just to think of the coefficient 3 and 4. Previously it was 2A plus 3B, coefficient 2 plus 3, that will be 5. It is 7, divisible by 7 for all AB belongs to Z. So you just examine if row is an equivalence relation on Z, or maybe question is like that, prove that row is reflexive, symmetric and transitive relation on Z. So this is yourself in exercise. Okay, so thank you so much. In the next class we will continue more problems on relation, and we will give you the equivalence classes